I was just moving this part, otherwise I could not see the slides.
Okay. Yes, yes. We can just
Okay, thank you very much. Good morning, everyone. Thank you for taking the time to attend this session. My name is Sandro Pinto. I'm Associate Research Professor at the University of Minho in Portugal. I don't know if you are familiar where Portugal is located, but in the south of Europe. You probably heard about Cristiano Ronaldo, is our best reference. I'm here to talk about edge intelligence, in particularly the activities among using AI, machine learning, and in the near future, Gen AI to secure tomorrow mixed criticality systems. This is pretty much the agenda for today. I will start with a brief introduction on the concept of mixed criticality systems. Probably you may not be aware about the term itself, but I'm sure you have seen and used many of these systems. Then I will explain how the computing platforms, in particular the microarchitectural of those computing platforms, have microarchitectural structures that can be leveraged to compromise either the safety on one side and also the security, because we are in the security workshop, right? But in these kind of mixed criticality systems, they are quite interlinked. Then I will explain how these structures can compromise either the safety by missing deadlines or even by leaking secrets in the concept of security. Then I will explain what kind of research we have been conducting in terms of using machine learning to either discover new issues from this point of view, and also how to use machine learning to also customize and configure the mitigation mechanisms to avoid these issues. And then at the end, I will just throw some ideas on how we plan to use Gen AI to configure these mechanisms. Okay, I will start from the beginning. Mixed criticality systems are those systems that require workloads or integrate workloads with different criticalities, okay? And the best example to explain is cars. Cars is a mixed criticality system because there is a trend nowadays which goes towards consolidation. And this is being driven in the industry by these so-called SWaP-C constraints, which means size, weight, power, and cost. The idea is to reduce as much as possible these requirements in order to build like more affordable systems, but at the same time more powerful systems. Cars are the perfect example, but we do have others that we are pretty familiar. We are talking about, for example, drones or UAVs are also a very good system, and also modern industrial control systems as well are other example. And so they are called mixed criticality systems because, as I said, you consolidate workloads or tasks of different criticalities. And one perfect example in cars is that on the same computing platform, the trend is towards centralized and zonal controllers. You may want to consolidate, for example, the subsystem for the airbag, electric power steering, and anti-lock braking, which are highly critical. And critical in the sense that if they fail, there is damage and there may be loss of lives. That's why the criticality of these systems are very high according to the certification standard, safety certification standard, which can be the ISO 262, and they classify like according to different ASILs, which stands for automotive safety integrity levels. ASIL D is the most critical, and examples in the cars are these systems. ASIL C can be, for example, the engine management. ASIL B can be like other subsystems in the car itself that are not so critical as the airbag or the anti-lock braking. And we can also have other subcomponents or subsystems that are not so critical, like the rear lights or the rear view camera, which, okay, if they fail, you may damage the car, but it's very likely that you don't damage lives. And then we have other ones like typically right now, which you also integrate the infotainment system of the car, which if the infotainment fails, you typically don't listen music or don't use the maps, but is not critical at all. And nowadays there is a trend to consolidate all of these components and systems in the same computing platform to basically save the swap C. Okay, this is just one example with a Tesla where you may find like all the different subcomponents that I was mentioning with all the different criticalities. Okay, and nowadays one technology that is highly used in this system is virtualization. I'm not sure how familiar you are with virtualization, but virtualization has been around for quite a long time, especially in the server domain for consolidation and power optimization. And you may have also used virtualization on your desktop when, for example, you have a Windows machine and you may want to run other operating system like Linux. Or if you do have, like I'm seeing here, the MacBook fans, if you have Mac and if you want to run for some reason Windows, you may install like a virtual machine in your desktop, which basically allow you to run other operating systems in one machine that was designed to run one specific operating system. And virtualization may have several shapes and forms, ranging from virtualization for the cloud, also virtualization for desktops, but the virtualization that we are talking here are virtualization for mixed criticality or embedded system, which may be quietly different. Well, creating small, powerful, lower consumption and cheaper solution is great, but this comes at the cost, and we will see what will be the cost of this. Well, as I said, virtualization is a key technology nowadays in also these mixed criticality systems because it allows to one side to guarantee the protection and the isolation of the different subcomponents, which if you want to comply with these safety standards and security standards for automotive, like ISO 26262, you may need to prove that when you consolidate one of those workloads from high criticality with one of those workloads with low criticality, they don't impact each other. And I'm not sure how familiar you are, but quite a few years back, there was this incident with the Range Rover, which basically an hacker was able, through the Bluetooth stack, to control remotely the car. And this was made possible because of this trend of consolidating either the infotainment and the communication stack with the basically engine management and all of these critical systems on the car. And this is very worrying, let's put it this way. So the trend nowadays is to use virtualization. You use the concept of virtual machines, and in these virtual machines you put different workloads, and these workloads have different criticalities, and you may end up with configurations like this from a computing platform point of view. And the problem with this integration is that on your computing platform, you have different resources, okay? You not only have the CPU, you may be familiar with the concept of CPU or central processing unit, which is what executes the workloads, but you do also have a memory hierarchy in your platform, which range from different level of caches, which are there in the computer architecture to accelerate execution, level 1 cache, also level 2 cache, and main memory. And these micro-architectural components tend to be shared across the different workloads. So, yeah, and in terms of isolation, you do have like spatial isolation, which you typically, when you use virtualization, you partition your platform in different resources and assign those resources to different virtual machines, which is happening here. But you do also have temporal isolation, which you guarantee that different subsystems execute in the right timing. Okay, but as I was explaining, the difference the difference is that if you use two different computing platforms to run the subsystems, which it used to be in the past, you are not sharing like these microarchitectural states and components, and you may have dedicated platforms for each system. But now with the trend of consolidating these different virtual machines in the same computing platform, you are ending sharing these microarchitectural structures, different levels of cache, and also different access to memory. Although each virtual machine cannot access the memory of each other because it's the principle of isolation and the principle of security. We have seen on the other day the SIA triad, the confidential integrity and availability. This is guaranteed by the isolation itself. But you may share like the access through the main memory controller, which basically creates interference between the different virtual machines. And yeah, shared, and shared may have a problem. And here we have a kind of more structured representation of what are these microarchitectural structures, and when you consolidate different workloads, you end up basically sharing these microarchitectural structures, which range from shared levels of cache and also the same memory controller. Okay, now let's understand what is the cost of sharing this microarchitectural resource in one computing platform from a safety but also from a security perspective. Because as I was explaining this in the concept of mixed criticality systems, they are quite interlinked. We used to say that there is no safety without security and vice versa, okay? Because they are highly interlinked. And what, from a safety perspective, is a fault-free operation is what we want, the goal is the desire. On security is the protection against malicious threat. How we typically see this is security is an external part that tries to create impact or change in the internal part of the system. Safety is an internal misbehavior that can have consequence on the external environment. It's typically how we distinguish safety and security, and they are quite interlinked. And the cause is that on safety, we can have accidental faults deriving from this shared hardware contention, or in the security, we may have intentional adversarial actions. And the impact on safety is a system failure or missing the deadlines, which may cause like damage for the environment and for the people. And on security, we may leak data or getting the system compromised, which is highly bad as well. And examples is that on safety, we may create interference among the different virtual machines, which may impact the execution and may lead to miss the deadlines of the real-time execution of the workloads. On the other side, on security, I'm not sure how familiar you are with the concept of side channel attacks, but a few. 1, 2, 3. I think we should be good now. Okay. But on security, we have a few years back some researchers from Graz that discovered this Spectre attack. This was quite unexpected discovery in the concept of security. They basically proved that by using shared microarchitectural states and microarchitectural optimizations in modern computing platforms, like branch prediction, speculative execution, plus like other microarchitectural structures, you could basically derive the secrets, not by accessing them directly, but by observing like the side effects of the execution of the computation. This was kind of the discovery of the century in this system security field. And they did this basically for Intel CPUs, but also for ARM CPUs and AMD. And my research group also did an outstanding discovery with Busted. Busted on microcontrollers, which are these small units that typically power the IoT. We presented this attack at the Black Hat Asia. Black Hat is like the most famous hacking conference in the world. It typically ranges from like, there is one in Vegas in the US, another one in Europe, and another one in Asia, in Singapore, all the time. And we were also covered by international press and media. And we basically discovered that it's possible to perform these side channel attacks on this class of CPU, which was not known as being possible as well. This is just a bit of context. Okay, so this is just the contrast between what are the mixed criticality systems, what are the impact in terms of safety, how these microarchitectural structures that are shared among the different virtual machines can have impact on safety and security. And so the question is, how can we uncover novel safety and security issues in the hardware itself? So as I said, in these computing platforms, we have different hardware resource, last level of cache, system bus, main memory. But like modern computing platforms are getting more and more complex. This is typically the diagram block of one of modern SoCs, system on chip. This one is from Xilinx, which embeds like silicon CPUs plus FPGA is the Xilinx UltraScale Plus. This platform is the ZCU 104, sorry. And typically what we see here is that apart from these three microarchitectural shared structures, there are even more and more and more. So despite the literature just reviewing some of them, we may be exposed to others that we don't know yet. Okay, and so what we typically do, or what typically the researchers do, is the so-called ad hoc methodology, which basically consists in reviewing like the existing research and the state of the art, okay, and then spending a lot of time to understanding how these components can be explored, and that may lead to very ineffective results, is very time consuming, and requires a lot of human power to do that. So what we have been doing is one kind of using machine learning to basically run experiments and try to uncover new issues that are not known. And because, so what we have been doing is constructing a methodology around running a profiling. We are using hardware components available on the systems on chip that are so-called performance monitor units, and they basically collect all the information happening inside the computing platform. And what we are doing is collecting, as Dr. Moncol mentioned, most important for machine learning is data, 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 data. So we are collecting and profiling the performance counters and the timing metrics for the system to construct a data set that is huge enough to understand what's happening. So then, based on this data, we create this feature extraction using variance analysis and correlation filtering to eliminate low signal features and try to select exactly what are the events that are more meaningful from this data set, so that we can basically derive an interference analysis and understand what are the patterns to basically identify when interference exists, which means that we may have a safety and security issue there. This is what we have been doing already, but these still have some shortcomings because it may lack semantic and contextual understanding because it depends a lot from the data that is collected and the accuracy is derived from this data, and which means that we need to spend an amount of time in doing the profiling. So what we are going to do now, or are doing now, is to try to leverage the generative AI to create some semantical awareness in this design, and to try to get a better system or more accurate system without depending on so much collected data, because this can become very unreasonable. So this was the part that we have been doing so far in terms of identifying new issues. And now, and at the same time, what we have been doing is thinking about how to use machine learning and how to use generative AI to basically configure and create more effective and scalable mitigations to prevent those. So for these specific problems that we have been discussing, in particular for these shared structures, there are already in the literature several techniques that can be used to mitigate these problems. For example, for the shared cache problem, there is this concept of cache coloring or cache partitioning, which basically allow you to split different cache ways or layers and dedicate them to different workloads of virtual machines, in the sense that you are not sharing them. At the same time, for the memory subsystem and the memory controller, there is a technique called memory bandwidth reservation, which basically allow you to get a portion of the bandwidth from the memory controller directly assigned to one of those virtual machines, in the sense that is not depending on the other virtual machines workload, and thus it cannot create interference and thus cannot create safety and security problems. Okay, in terms of cache coloring or partitioning, it basically consists in assigning different virtual colors or virtual ways to different virtual machines, and thus avoiding that these workloads compete with these workloads in accessing the shared cache structures. It's like you have 8 pieces of a cake. Instead of getting 10 people to compete for the 8 pieces, you allow and give like these 4 pieces to 5 people and these 4 pieces to the other 5 people, and then you avoid these 5 people to fight with the other 5 people. In abstractly, it's more or less what we do. But this has a problem in terms of, these are some results in terms of performance execution. This is benchmarks. The first bar is basically the system executing without interference. And then, for example, this I bar is when the other system is competing for the same resource, which basically creates an enormous impact on the performance. And then the other bars are just implementing, for example, this last bar is just when we have this kind of mitigation in place, where we can minimize the impact of this interference. The problem with this technique is that it may be effective, but depends a lot from the workload and also from the configuration. Okay, which means it may or may not be effective. And the problem is that when you are configuring, depending on how much cache sections always you have, and depends how much virtual machines typically you have on your system, you may end up, and these are just benchmarks for different configurations, and you see like the bars, the higher they are, they basically, the worst is the mitigation effect, which means that for the same technique, depending on the configuration, you may have different behaviors, which mean that it may be more or less effective. The problem is that depending how much cacheways you have and depending how much virtual machines you have, you may end in many different possible configurations. Just to give you an example for this red line, okay, for 8 virtual machines with 16 cacheway, you may end up with 6,435 different possible configurations. Of course, if you are doing this like by hand or trying to perform the tuning yourself, you may end up in a very non-optimized system. And that's more or less the takeaway we take from here. Like using manual intervention or the people intervention to configure this mitigation technique may lead to very inefficient results. So what we have been doing is that's basically what explains here. Ad hoc methodology requires deep architectural knowledge and is very timing and labor intensive and may become very ineffective. So what we are doing is using machine learning again to configure these mitigation techniques, and we are doing in 2 ways. First, we are doing, and we have here more or less the representation with the feedback loop. And we are doing this at design time, which means when you are building your system, you run this machine learning to tell you, okay, according to these workloads, the most optimal solution is this one. Okay, this is the so-called at the design time. But the design time means that when you deploy your system, you cannot adjust or fine-tune the parameters, which means that during runtime, if any external behavior gets into the equation, you basically are not prepared for that. So what we are doing right now as well is that we are also using machine learning in the runtime execution, okay? And for that, there are, as Dr. Moncol mentioned, like one enabler for machine learning and AI is this high-performance computing, and the 2 enablers that we are exploring in terms of allowing like this kind of methodology possible at runtime execution is from one side the use of FPGA technology. FPGA basically allow you to deploy in kind of silicon with software, with the kind of HDL language, the behavior of you typically write in an ISA on a CPU. It's one enabler. The other technology enabler is the use of RISC-V as a computer architecture, because RISC-V, comparing to ARM and Intel, is customizable, which means that you can basically create customized instructions so that you can model your, or enable, have a model to enable your machine learning model. Okay, and then our next step here is also to use generative AI to inject semantic and context-rich scenarios in the training loops and try to generate edge case on the adversarial workloads. The problem is that reinforcement learning is still not integrated in the pipeline and is still under development, which may hamper also a little bit the effectiveness of this generative AI. So, as a final takeaway, this is where our research is heading. In particular, we are trying to understand how this Gen AI can unveil safety and security issues and accelerate research and support these configuration mitigation techniques. And I'm just dropping here a few points. I think it's very important, Gen AI, because to unveil either vulnerabilities or issues itself, because it can create novel scenarios that we don't anticipate and that we didn't think of. And these micro-architectural architectures on this computing platform are super complex, which means that we need some sort of intelligence that goes beyond what we think. It enables like the fast iteration and generation of test case across the different layers to build more reliable systems, and can support very complex mitigation configurations. As I was explaining before, we have the design space of the configuration setup can be thousands and thousands of different possibilities, and thus we need this sort of intelligence to cover all the corner case. And it can link like low-level hardware behavior with high-level application demands, creating an holistic analysis, and of course reduce significantly the tuning effort and the exploration time, because it doesn't depend on time consuming from people itself. Okay, I just finished a little bit earlier, but I think we will have much time for questions.
So thank you very much, Dr. Sandro, for the comprehensive presentation on the mixed criticality system and how AI can enhance to more safer and secure system. So now we open the floor to Q&A session. So if you have any question, please kindly raise your hand. I'll pass the mic to you. For those who are joining online, if you have any questions to Dr. Sandro, you can kindly unmute yourself, raise your hand, or type in the chat box. Thank you very much.
So the optimization you say it's on runtime, right? So I have a question. If one of the VM run on the running RTOS, so would you ML or like a optimization process run before RTOS? Like RTOS is like a real-time boundary, right? Yeah, of course. But you say that like your model gonna deploy on runtime system, right? On like live hot. So I wonder like, would your system run like configuration for RTOS as well, or it should be like separate model?
Yeah, the question is when we have this runtime component that basically optimize like all the configuration of this micro mitigation mechanism is performed, if it should be placed on the real-time operating systems or where it should be, right?
Can I get it again?
So the question was for this runtime execution, okay?
Yeah.
When I said that basically we have these mitigation techniques and we are using like AI, and we are doing it in two ways. First way is like a design time, and then the second way is during runtime. At runtime, basically we may have a system which may have a real-time operating system side by side with a general purpose operating system like Linux, okay? And your question was basically, for which is this runtime execution component if it configures the real-time operating system, right?
Yeah.
Yeah, so you need to think that this runtime mechanism is a mechanism to configure like the mitigation techniques from the hypervisor perspective, which means it doesn't necessarily touch on the real-time operating system, because the operating system runs in a VM, and for the hypervisor, the VM is a kind of black box. So what we are really concerned about is how we split these micro-architectural structures, in particular cache lines on the shared L2 cache, and how much of them we assign, for example, for the real-time operating system, and how much we may assign to other VM like that runs Linux. This will impact then the performance of the real-time operating system itself, but how you configure the real-time operating system is up to you, because for the hypervisor perspective is a black box.
Yeah, but so follow-up question.
Please.
So, like, but would your optimization process be faster enough for the RTOS requirements?
If
like the optimization process ML, generative AI one, would it be faster enough for the RTOS requirement?
Not necessarily, because the RTOS, you need to think that these kind of systems, we are not just running one RTOS. We are running like multiple virtual machines. And you may end up running like one RTOS, one Linux, multiple bare metal virtual machines. So if you just configure the RTOS, okay, you are basically disregarding whatever happens with the other virtual machines. And these other virtual machines may impact or may create interference and impact in these microarchitectural structures that then impact the RTOS. So you need to look at the system from an holistic perspective, and that's the part that is difficult at some point when we explode a lot in the number of configurations, how this reflects from a real-time operating system perspective, which in this kind of mixed criticality is what matters, because is what gives you the real-time requirements. But these very nice questions.
Thank
Means
you
you
for your
understood
question,
the
sir.
presentation.
Thank you for your question, sir. Answer, sorry.
I think we have one gentleman on the front.
Thank you, Dr. Sandro, for the great presentation. I want to ask about the shared hardware architecture, because it is the criticality is different, right? As you present, are the shared hardware architecture is common to adopt it for the equipment we use, or is there any the different architecture which they separate with is the criticality which is high, they has on hardware?
Yeah, it's a very nice question. The question is about if this kind of architecture where the computing platform is shared is common in these systems. My answer to you is all the industry, especially the automotive one, is shifting towards what was called federated architectures, which is exactly what you see here on the left. Each subsystem will have a computing platform dedicated so that they cannot interfere with each other. This was the trend 20 years ago. But nowadays, because of this big pressure in terms of SWaP-C, size, weight, power, and cost, like cars, for example, are building exponential in terms on the number of features. If they would put one platform for each feature, it's impractical. It's not possible. So to save in all these metrics, these car manufacturers, and 100% guarantee I work with a couple of them, they are resorting to these kind of modern high-performance computing platforms where you may end up having these multi-core architectures with a lot of computing units and everything on the same platform. But the problem is that when you do that, you have these shared architectural components, and then you need to deal with these kind of technologies and all of these issues. But this is something that all the car manufacturers are now shifting towards that. And I had projects with Ford, with Minho. I just came from China to meet with some of them, so they are all doing those. But thank you for the question.
Do you have any further questions? We still have time.
People want to
Fast
break.
break here. Let me check online. Okay. So I believe that everyone is looking forward to the break. So let's have a tea break, and then we will resume at 10:30. So it will be a long break. So thank you very much once again, Dr. Sandro, for the comprehensive presentation.
Thank you very much.